Consider the two-dimensional motion given by the position vector, vector r of t, with components 2 cosine of t, 2 sine of t, where t is greater than or equal to 0, less than or equal to 2 pi. And we're asked here to sketch the trajectory or sketch the path of the object. Part B asks us to then find the velocity and the speed of the object. And last but not least, Part C asks us to find the acceleration of the object. So the first thing that we want to do is sketch this trajectory, sketch the path of our object in motion. So what I want you to do is recall that if you have a circle centered at the origin with a radius of the absolute value of r, so something like x squared plus y squared equals r squared. And again, this is the center point is at the origin, 0, 0, with a radius length of the absolute value of r. These Cartesian coordinates map to the parametric equations as follows. So the parametric equations of a circle for some arbitrary parameter t, so for a real number t, we have that x of t, the parametric description of x, is defined as the radius r multiplied by cosine of t. The y, or the parametric description of our y variable, is defined as r sine of t. And if this is, we'll assume that we have counterclockwise orientation. This is where t is greater than or equal to 0, less than or equal to 2 pi. So looking up at our given position vector here, we realize that we have, or the trajectory, the path of our object is a circle. So for part A, again, we want to sketch the path of our object. So again, looking at our position vector, if we take x of t and square it, plus y of t and square this. So let's plug in the components of our position vector. This is going to leave us with 4 cosine of t squared plus 4 sine of t squared. And we have a greatest common factor here of 4, so we can pull that 4 out, which leaves us with 4 multiplied by cosine of t squared plus sine of t squared, which we realize is Pythagorean's identity. Woohoo! We know that this, of course, is equal to 1, which leaves us with the equation of a circle. We have this x squared plus y squared is equal to 4. So our trajectory is a circle centered at the origin with a radius of 2. Woohoo! So we're ready to go ahead and sketch this. So giving ourselves more room. So if you have graphing paper, it's always helpful to use. Otherwise, just be sure to label. This is not art class, so we'll just try our best and label. So here we go. Here is the Cartesian coordinate system. We have the y-axis and the x-axis. And now we have our trajectory, or the path of our object, is a circle with a radius of 2. So here we go. Say there's 2 on the x and y axis, and we're moving in a counterclockwise direction around our circle. And so this is our parametric description of the circle vector r of t, where x of t and y of t are defined as 2. Cosine of t is our x coordinate, and y of t, the parametric description, is 2 sine of t. And this is for, we have a complete circle here, so this is for t greater than or equal to 0, less than or equal to 2 pi. So this is the path of our object in motion. All right, so we are ready now to go ahead and find the speed and the velocity vector for the object in motion. So before we can find the speed of the object in motion, we need to find the velocity vector. So we can recall that the velocity vector is the rate of change of the position vector. So using our position vector here, we are differentiating, which leaves us with minus 2 sine of t and positive 2 cosine of t. And there's nothing wrong with this. We can leave that vector as it is. Or since we know we're finding the speed of the object in motion, we could pull a scalar multiple of 2 out. So we have 2 times the vector minus sine of t cosine of t. So here is our beautiful final answer for the velocity of the object in motion. And now to find the speed of the object in motion, we need the magnitude of our velocity vector. So we can keep our scalar multiple of 2 on the outside. And so we have minus sine of t squared, which gives us sine of t squared, plus cosine of t squared, which is cosine of t squared. And hey, there's Pythagorean's identity again. Woohoo! So we know, of course, that that goes to 1. So this leaves us with a speed of 2. So we can see here that the velocity has a constant magnitude. We have a constant magnitude, a constant speed. And just for fun here, now that we have our velocity vector, let's think about what's going on at different points of the circle. Right, so looking back up at our trajectory here, let's think about when t is equal to 0. What's our velocity vector going to be here? So the velocity vector when t is 0, we're going to have 2 multiplied by sine or minus sine of 0, which gives us 0. Cosine of 0 is 1. So hey, that's a unit vector pointing in the positive y direction, multiplied by that scalar multiple of 2. So we have, think of our velocity vector here, we'll use green. So it's pointing up in the positive y direction. So this is the velocity vector, and shame on me for forgetting my hat. That's the velocity vector where t is 0. Now what about, let's do another one. Let's say where t is equal to pi by 2. So here's that point. T is equal to pi over 2. What's the velocity vector doing there? So we have the velocity vector at pi by 2. So this is going to be equal to 2 multiplied by minus sine of pi by 2, which gives us a negative 1. And cosine of pi by 2 is 0. So this is a unit vector pointing in the negative x direction, multiplied by that scalar multiple of 2. So we have minus 2I hat. So here, if we sketch this velocity vector, we can see it has a different direction. So this is the velocity vector when t is equal to pi by 2. And we can continue doing this. We can see that at every point on the circle, the velocity has a different direction. And I should have labeled this. So this point here that we just drew in purple, that's your velocity vector at 3 pi by 2. So it's a vector of length 2 pointing in the positive x direction. And the previous one, this is our velocity vector at pi. So it's a vector of length 2 pointing in the negative y direction. So we can make a little love note here to ourselves that the velocity vector is always changing direction. So it has a constant magnitude, but the velocity vector is always changing directions. So it is continuously changing directions. All right, so last but not least, we now need to go ahead and find the acceleration. So part C, we want to find the acceleration vector, vector a of t. And we can recall that the acceleration vector is, of course, the rate of change of your velocity vector. Or in other words, the second derivative of the position vector. So looking at our velocity vector, this is leaving us with, keeping that scalar multiple of 2 on the outside, we have 2 multiplied by the vector minus cosine of t minus sine of t. And just for fun here, if we play around with these scalar multiples, notice in this answer we have 2 on the outside and the common scalar multiple of -1 on the inside. If we play around with their positions, if we pull that negative to the outside of the vector and redistribute 2, what are we left with? And let's give ourselves a little bit more room. So again, we're switching the scalar positions. We have the negative on the outside and we've redistributed 2. So this is minus the vector 2 cosine of t, 2 sine of t. And we realize, hey, that is the negative of the position vector. Woohoo! So what is this telling us? So this is, first of all, our beautiful final answer. Any one of these. And this is letting us know that the acceleration is always the negative of the position vector at all times. So we can say that the acceleration vector is the negative position vector at all times t. And so that is our beautiful final answer.